So, welcome. In this video, I want to talk about or present a microscopic view of what happens inside a dielectric material. So this is kind of a complementary perspective to what I was describing last time, which is kind of the bird's eye or maybe more practical aspect of dielectric materials. Today, I kind of want to give a sense of where or what's happening kind of at the atomic scale, at least qualitatively. Okay, so we were talking about dielectric materials before, and which are just, could be anything that you put in, say, in a capacitor, but really it could just be any material, and we're really thinking about the way that materials just react and respond to electric fields. So, okay, so if we had a capacitor, and it can be hooked up, well, even before we hook it up to a material, or up to a battery. And you could imagine you fill the gap with some material, and that material is made of little atoms. So we'll just imagine that there are little atoms, which we will model as kind of little spherical balls. Okay, and we'll go ahead and say that the atomic number is Z. The atomic number tells you the number of protons on a nucleus. Okay, so Z tells you how many protons there are in the nucleus, and it also then would, in a neutral atom, would tell you how many electrons there were. Okay, so now let's think about what happens to this material if you were to hook up the capacitor to a battery. So you apply a voltage across this capacitor, which is going to generate an electric field, which will run from one side of the capacitor to the other. So if you were to do that, if we were to hook this up to a battery, then all of these little dipoles are going to shift. So if we hook up a battery, let's say we have the plus side here and the minus side there, you're going to generate some electric field lines like this. And then the little atoms are going to polarize into dipoles. And the negative charge will go one way and the positive charge will go the other. So I'm going to say negative charge is going to move towards the plus side, and the plus charge is going to go the other way. And here I'm going to have minus and plus, minus and plus, minus and plus. That. Hopefully that's kind of clear what's happening. All right. So in particular, because this is going to come up here later, if we were to pull out a typical sort of dipole, it would look something like this. And if we labeled the separation on average between the positive and negative sides, we'll call that A. That's going to be a vector running from, the distance vector running from minus to plus for a typical atom. Okay? So one thing I want you to notice, right now I'm talking about the effect of the external electric field on the little atoms, polarizing them. But notice they are going to be little dipoles after polarization. And so they are going to create their own electric field. And if you notice, on average, the induced secondary electric fields are going to run from positive to negative. So you'll notice that the secondary electric field actually is kind of oriented opposite relative to the external electric field created by the battery or whatever voltage source. So that's the sense in which, that's why we call these dielectric materials, because they create internal electric fields which work against the external electric fields. They oppose it. So the primary electric field goes to the right, but the induced kind of secondary electric field goes back to the left. Now, in practical terms, the induced electric field is going to be much smaller than the primary electric field. And so it tends to just be a small reduction of the electric field. But that's the origin of the word dielectric. The secondary dipole moment kind of works against the primary electric field. Okay, so keep this picture in mind. This is what's happening inside a dielectric material. Let's put a little bit more to this. So what we could imagine is that, so if I had an external electric field, and if I wanted to keep track of the polarization it induces on an atom, like that, and the separation distance is we're going to call it A. So you might remember we had, so this is a dipole with the charge separation given by a quantity called, the distance is called A. We had a vector called the dipole moment vector, P, and the formula we had for P was that P vector equals the charge, it's actually the positive amount of charge. Well, that's nothing other than the atomic number, Z times E, times the distance, the separation vector, which we're calling A vector. So lowercase p is the dipole moment vector for an average atom. Basically, that's determined by chemistry, or really it's determined by quantum mechanics. But it's some number, some polarizability which characterizes different atoms. Okay? So what we want to do is relate, to kind of understand how the atomic features become the measurable features, then we want to relate this microscopic atomic dipole moment to macroscopic quantities over the whole slab of a dielectric material. Okay. So to do that, we do the following. We introduce N, which tells you the number of atoms per unit volume. So it's some sort of a concentration or number density. And then I can define the polarization vector capital P, and that's going to be defined as the number of atoms per unit volume times the polarization per atom, which is just a dipole moment. So it's going to be the number of atoms per volume times the polarization per atom. So the units come out as polarization per volume. This is nothing other than N times the dipole moment vector, the lowercase p. So capital P is the number of atoms per unit volume times the polarization per atom, which is the dipole moment vector. Okay, so that's kind of a useful quantity to define. This is a macroscopic quantity because it takes it kind of averages. Well, it counts how many atoms per unit volume. So yeah. All right, it's an averaged quantity. Maybe that's a better way to say it. Oh, dang it. All right, so let me rewrite that then. Because I know that P is equal to Z P vector E times A, and then capital P is going to be in Z E A. All right, very good. So now let's kind of think about what happens when you have a capacitor and you have all these little and you apply an electric field to it, and you get all these little dipoles rotating around. Let me change colors. So on the outside, I have plus charge, and I have minus charge there, and then on the inside, I get some negative charges here and plus charges here. And what you should imagine is that, in fact, the atoms reorder and twist around, and in the middle, basically, they're going to overlap. So you could imagine something like this. I'll kind of draw in a fifth little blob. Okay, and so what you could imagine is in the interior, everywhere there's a plus charge, right next to it there's going to be a negative charge. So in the middle, there's basically no appreciable charge. However, if you were to zoom in very close to one of the plates, you would find a thin layer of charge all along it. So near the positive plate, you would get a thin layer of negative charges, minus, 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 minus. And near the negative charge, you would get a thin layer of plus charges all around that edge. Plus, 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 plus. Okay? So what we could do is sort of quantify this effect and ask, okay, how much charge do you actually get along the edge? Kind of what's the boundary layer of charge that you get? So we'll call that the surface charge. That would be that. So what we're really doing is asking. So these kind of atoms polarize in the middle, they kind of cancel out, and we're left with a thin layer on the edges. A thin layer of negatives over here and a thin layer of positives over here. Okay? And we want to know what is the kind of induced surface charge that builds up because of polarization. Okay, well, the way that would go is you would say, okay, the surface charge would be the number of atoms so the number of atoms per volume times the charge per atom times the volume of the surface layer. Well, okay, so the number of atoms per unit volume, that's this parameter N that we've already seen. The charge per unit atom, well, along the boundary layer, each atom there contributes Z times E. And finally, what's the volume of that boundary layer? Well, I mean, it's hard to say exactly, but it's roughly going to be the area of the capacitor times the polarization vector, because that's roughly how thick, that should set the scale for the thickness of that layer. So it should be the area of the capacitor times the size of the polarization vector. Okay, so that should be the amount of surface charge that develops along the surface of the capacitor. And rather than talking about surface charge, we usually talk about surface charge density. So I want to divide that by area. So that would give me sigma, which would be the polarization charge density, surface charge density, would be the surface charge per unit area. So that's going to just be the number of atoms per unit volume times the charge per unit atom, or per atom, times the volume of the slab divided by the area. So the areas cancel, and I just get A. Aha! But that's nothing other than the magnitude of the polarization vector. Okay? So this is kind of how you can get it. This is the perspective on dielectric materials as to what's really happening on the inside, and it's relating the microscopic quantities A, and E, and Z to the macroscopic numbers that you get in the end. If I can. Yeah, okay. So, so when you go through, yeah. We have this. And then, all right. So now last time I described how you could relate or the effect of a dielectric material by simply changing the value of epsilon naught and replacing it with epsilon, where epsilon equals kappa E times epsilon naught. So this is the epsilon naught is the permittivity of free space or vacuum. Epsilon would be the permittivity of the material. Kappa is called the dielectric constant. Okay? It turns out it's useful to think about kappa, the dielectric constant, for a lot of materials. You can kind of think of it as roughly, to first approximation, maybe nothing really much happens, and then there's kind of then the dielectric in the material is sort of a small deviation away from the vacuum value. So you can write kappa E as 1 plus hopefully a small number, a small correction. So you're saying basically, in this number here, chi is called chi is called the susceptibility. Okay. Chi is the dielectric susceptibility. And what it does is it measures the deviation of the kind of the deviation away from vacuum. Okay. And it turns out, I think I was going to go through the derivation. I really don't see any point to this. It turns out that chi can be related to the polarization vector. So the polarization vector, P, capital P, which remember we said was N times Z times E times A, it turns out that that is related to the electric field you have in the presence of the dielectric material by the following formula. Epsilon naught times chi E times the electric field in the presence of the in the capacitor. So the idea is that the polarization vector, well, that measures how much polarization has occurred. So that's, and polarization would be a change away from empty space. So P knows about the change away from empty space. And in that same way, chi also knows about the deviation away from empty space. And so this kind of pulls together the dielectric constant that I defined last time with properties of atoms and molecules and stuff. Okay, so anyway, you really just need to know, there's really just some number. So I think some of the sapling questions will just say that the susceptibility is blah, blah, blah. That's that. When you want to actually go to use it, normally you don't really care too much about the susceptibility, at least not in this class. Instead, what you want to do is add 1 to it to get the dielectric constant, and then that's what multiplies the permittivity of free space. Personally, again, in this class, most of the time, you can just pretend that you're in vacuum, and then at the very last second, replace epsilon naught with epsilon by just multiplying by the dielectric constant. And it's really that simple. Okay, so that's kind of the microscopic view on what is a dielectric material. The other thing I wanted to do is to kind of talk about what happens there. And so remember, capacitance, C, is always something which is some sort of geometry stuff times epsilon naught, or in the presence of a dielectric material, times kappa epsilon naught. So if you think about it, so if I have a capacitor, and I say that Q is equal to C times V, right? So, and kappa is bigger than 1, right? It's going to be bigger than 1. So what that's saying is that, there's a couple ways to say it. Either you're saying that for a fixed voltage, you get more charge because kappa is bigger than 1, and so therefore C is increased. Or you're saying that for a fixed charge, you actually get less voltage. That actually ties into the picture I had before, because what you're seeing here in these, it's kind of like this. You have a capacitor, and The external electric fields I'll put in blue. So I have a plus charge and minus charge. And then the dielectric materials, actually their electric fields on average work backwards. They're not as big, but they work backwards. And so that what happens is, for a fixed amount of charge, the total internal electric field is actually reduced because the dielectric material shrinks or reduces the total electric field, and that has the effect of shrinking the voltage. So for fixed charge, increasing the capacitance actually reduces the voltage, and what that really tells you is you're reducing, for fixed charge, you're reducing the electric field. Now, in practice, we don't usually work with fixed charge devices. And most of our devices, we use power supplies, which actually, instead of controlling the charge, they control the voltage. So most of the time, you have a battery or a power supply which controls the voltage and fixes that to be a definite number. And therefore, increasing the capacitance actually just increases the charge, which is accumulated. Okay, so that's what I wanted to cover in this video. Hopefully that clarifies how capacitors really work.